Hi everyone. So we are at module 5, and in this module we're going to look at the solution of linear time invariant state equations. We're going to look at two approaches to solving the state equations, and then we're going to introduce something that we call observability. So let's start. Let's consider a linear time invariant single input, single output system that is described by state space representation x dot equal a multiplied by x plus b multiplied by u, and we have y that is equal c multiplied by x. And what we are interested in, we want to solve for x of t and for y of t. Now what we can do, we can solve for x of t using Laplace transform. And therefore, if I take the Laplace transform of the first equation, I'm going to get s multiplied by x of s minus x of 0 equal to a multiplied by x of s plus b multiplied by u of s. Now we can solve for x of s. Since we have x of s on both sides, I'm going to move a multiplied by x of s to the other side. So I'm going to get s multiplied by x of s, which I can write as s multiplied by I multiplied by x of s. I can always multiply by the identity. Minus a multiplied by x of s equal to x of 0 plus b multiplied by u of s. Then I can take x of s as a common factor. I'm going to get s multiplied by I minus a multiplied by x of s. And this is equal to x of 0 plus b multiplied by u of s. Okay. So, but I want to solve for x of s, so I can just say x of s, I can multiply both sides by the inverse of what multiplies x of s. So this is going to be s multiplied by I minus a inverse multiplied by x of 0 plus s multiplied by I minus a inverse multiplied by b multiplied by u of s. I hope this is clear. I multiplied both sides by si minus a inverse. On the left side, that's going to give me identity and therefore just x of s, and on the right side is going to multiply the inverse. Okay, so this is what x of s equal in the Laplace domain. Now what I'm going to do to simplify the write-up and the notation, I'm going to define the state transition matrix as phi of t, and this phi of t is going to equal to the Laplace inverse of si minus a inverse. So what I've done, I've taken this, and I said I'm going to define the inverse of that in the time domain as the state transition matrix, because if I multiply, you can see if I multiply by the initial condition, it gives me how the states are changing with time, how the states are transitioning in time. So therefore, I define phi of t as the Laplace inverse of si minus a inverse. Okay, so therefore I can go back to my equation and take the Laplace inverse of this equation here. So therefore Laplace inverse, of this equation here, Laplace of x of s, Laplace inverse of x of s is equal to Laplace inverse of si minus a inverse multiplied by x of 0 plus Laplace inverse of Si minus A inverse multiplied by B multiplied by U of S. I just taken this equation, x of S, and I've taken the inverse Laplace transform of it. Okay. So if I do that, I'm going to get the inverse Laplace transform of x of S, which is x of t. And if I take the inverse of Si minus A multiplied by x of 0, this is going to give me phi of t multiplied by x of 0. And if I take the inverse, of course, x of 0 is just a constant. So when I take the inverse Laplace, it's going to be whatever the function of S, which is the Si minus A. X of 0 is just a constant. And remember, the Laplace is a linear operation. So just is going to multiply the inverse by x of 0. However, on the second term, I have a function here and another function. I have two functions that multiply by each other. This is one function and this is one function. Now I know multiplication in the Laplace domain, what is it going to be equivalent to in the time domain? Is going to be convolution. So when I take the inverse of these two functions multiplied by each other, in the time domain, that is going to be the convolution. Okay, so therefore, if I come back here, phi x of t is going to equal to phi of t multiplied by x of 0. Again, x of 0 just a constant, plus phi of t multiplied by b. B is just a constant. However, now I'm going to have to convolve that multiplication by u of t. Remember, multiplication in the time domain, in the Laplace domain, in the S domain. Multiplication in the S domain is convolution in the time domain. So since these two functions I have in yellow multiply each other in the S domain, in the time domain these going to be multiplication with each other. Okay, so let's write this down. X of t is going to equal to phi of t multiplied by x of 0 plus, this is the convolution. What is the convolution? I can write this as the integration from 0 to t, phi of t minus tau multiplied by b multiplied by u of tau d tau. This is tau, and the integration, the variable is t. So after I do the integration, I substitute from 0 to t. Now if I look at this expression, this gives me the states as a function of time. I can immediately realize this is the response that is due to initial conditions. So this is my response due to initial conditions. And I can also immediately see that this is the response that is due to the input. Okay, so this is the result that we are looking for. Let's just put it in a box. And look at it and see what happens when t is equal to 0. So let's do a sanity check. Make sure that what we got is correct and build on that some observations. So if I take at time t equal to 0, I am at the initial state, we must recover the initial conditions. So basically what I'm saying is if I take x of t and substitute t equal to 0, this is going to give me x of 0 But what does the equation give me? It tells me that this is going to equal to phi of 0 multiplied by x of 0 plus the integration from 0, t is 0 because I'm calculating at t equal to 0, phi of t minus tau multiplied by b multiplied by u of tau d tau. Now this term on the second term, this is just going to equal to a 0 because I'm integration from 0 to 0. But looking at the first term, so what I'm getting here is x of t when t is equal to 0 is equal to phi of 0 multiplied by x of 0. But on the left side, I have x of 0 here. This is x when t is equal to 0 is nothing other than x of 0. How could this be true? The only way this can be true is if phi of 0 is equal to the identity. So therefore, we conclude that this means that we must have phi of 0 equal to the identity matrix. So therefore, this transition, the state transition matrix, if I substitute at t equal to 0, it should give me the identity. Okay. So let's do an example and illustrate this calculation. So going back to our mass damper. Oh, sorry, this is another. Let's do another example. Let's consider a single input, single output system that is x dot equal to -1, 0, 0, -2 multiplied by x plus 1 multiplied by 0 multiplied by u, and y is equal to 1, 1 multiplied by x. I mean, notice here we have a D matrix, but the D matrix is equal to 0. D is the feed forward matrix, which means if there is a direct connection between the input and the output, then we will have a D matrix. Most of the system that we're going to be seeing, D is going to equal to 0. There's not going to be an input that is directly connected to the output. So if anybody is, confused, or it's like, oh, you at one point you mentioned D and you never used it, why is it we're not having D? Again, we will have D if the input is connected directly to the output. In most cases, D matrix is equal 0. But in case we have a system that there is this feed forward, we can't accommodate it. Okay. So this is our single input, single output system. And if we let u of t equal to a unit step function, we want to calculate x of t and y of t. And of course, I did not mention before, if I calculate x of t, then I can immediately calculate y of t, because y is just c multiplied by x. If I know the states, I can multiply and get y of t. Okay. And of course, one more observation. Notice here, when we give the initial conditions, we only give it the initial conditions for the states. We do not give the initial conditions for the input, because the input is known. I know the function of the input. The input is known. There is no initial condition. X is unknown, but I know what it started from, the initial condition of x. U of t is a function that I know all the time. Okay, so the first thing I'm going to do is I'm going to calculate the state transition matrix. I'm going to calculate Si minus A inverse, which is equal to Si, since this is a 2 by 2, I'm going to take the 2 by 2 identity multiplied by S, 0S minus A, which is -1, 0, 0, -2. And I want to calculate the inverse for this. Now, I hope this might be new to some and might be confusing to some. But nevertheless, hopefully, the more we see it, the more it becomes intuitive. how I took S multiplied by I minus A. When I have S multiplied by I minus A, I is the size of A. If A is 2 by 2, then I is a 2 by 2 identity. Okay, what is this equal to? S minus minus 1 is going to give me S plus 1. 0 minus minus 0 is a 0. 0, S minus minus is going to give me S plus 2. And I need to calculate the inverse of this. Now the inverse for this matrix happens to be simple. Just because I only have the diagonal terms, I can immediately find it. And that is going to equal to 1 over S plus 1, 0, 0, 1 over S plus 2. And you can immediately see that if I multiply this by this matrix by this matrix, I'm going to get the identity. S plus 1 over S plus 1 is going to cancel. And then when I multiply S plus 2 multiplied by 1 over S plus 2, I'm going to get a 1. But in general, we know how to calculate the inverse of the matrix. Okay, so this is what Si minus A equal to. Now I'm going to calculate phi of t, which is equal to the inverse of Si minus A inverse. And therefore, I'm going to have to take the inverse Laplace transform. And that is going to equal to, what is the inverse of 1 over S plus 1? This is going to give me e to negative t. This is a 0, and this is going to give me e to negative 2t. Now also, we can do a sanity check here on the side. If I substitute t equal to 0, what am I going to get? I'm going to get phi of 0. If I substitute t equal to 0, I'm going to get 1, 0, 0, 1, which is the identity. So that checks. Okay. So now I can go to the equation that we had above here, and I can calculate x of t. What is x of t going to equal to? X of t is going to equal to phi of t multiplied by x of 0 plus the integration from 0 to t, phi of t minus tau multiplied by b multiplied by u of tau d tau. Now, since the input is a unit step, and therefore, so again on the side, this u of tau is gonna equal to a 1 when tau is greater than or equal to 0. It's a unit step. And therefore, I can, in this integration, this is just gonna equal to a 1. So I can come here and say this is gonna equal to phi of t, which is equal to e to negative t, 0, 0, e to negative 2t, multiplied by x of 0, which is given as negative 1 and a 1, and then plus the integration from 0 to t, and phi of t minus tau is gonna be e to negative t minus tau, then 0, 0, e to negative 2 multiplied by t minus tau, and then multiplied by b, and the b matrix was equal to 1, 0, and we're going to multiply these and then take the integration. Okay. So again, this notation might be new to some. Hopefully this will clarify what these equations above. With the example, it will be clear as to how we use them and what they mean. Okay, so continuing, if I to multiply this matrix 2 by 2 by 2 by 1, I'm gonna get this multiply, I'm gonna get a 2 by 1 matrix. So the way we multiply it again is we're going to take this row, multiply it by this column, this multiplied by this term, 0 multiplied by 0, and then I'm gonna take this row and multiply it by this column. The 0 multiplied by the 1, e to negative 2t is gonna multiply by a 0. Does that make sense? Okay, so continuing and multiplying the first terms, the same thing. This row is going to multiply by this column, this row is going to multiply by this column. So therefore, I'm going to get e to negative t. This is e to negative t, and then multiplied by the negative 1. And the second term is going to be e to negative 2t, because it gets multiplied by the 1, the positive 1, plus the integration from 0 to t of, when I do the multiplication, I'm going to get e to negative t, and I can write this as e to tau. This is the same as writing e to negative t minus tau. I just, I just separated the terms. And then when I multiply the second row, 0 is going to multiply by the 1, e to negative 2t multiplied by a 0, that's going to give me a 0. So therefore, I'm going to have a 0 here, and this is d tau. Now, the way we do this is we integrate each term. And therefore, I can come here, I have negative e to negative t, e to negative 2t, plus the integration of e to negative t multiplied by e to negative tau, e to tau, and we are integrating over tau, not over t. So e to tau d tau. If I integrate e to tau, it's just gonna give me e to tau, and that is the limit of the integration from 0 to t. Does that make sense? Remember, when we're integrating when we're doing the convolution, we're doing d tau d tau. So the integration, we're integrating the over tau. Okay, the second term is going to be 0, and therefore I can write this as negative e to negative t, e to negative 2 multiplied by t, plus, if I substitute from 0 to t, I'm going to get e to negative t multiplied by e to t minus e to 0, which is a 1. T is going to give me e to t, 0 is going to give me, I substitute 0 in tau, is going to give me a 1. Okay, the second is a 0. Now I can put these together to get x of t, and that is going to equal to, I have the 1 here. Okay, if I multiply e to negative t by e to t, that is going to give me a 1. Again, this is this multiplied, this multiplied by this. E to negative t multiplied by e to t is going to give me, a 1. Okay, and then I have e to negative t multiplied by 1, and also I have e to negative t. I have 2 e to negative t, both with negative sign. These both gonna give me negative 2 e to negative t. Make sense? So let me mark them. So I have this term and I have the result of the multiplication of e to negative t with -1. Two of them, they're going to add up to -2 e to -2t. And then I have e to -2t, I'm adding to it a 0, and that is going to give me e to -2 multiplied by t. So here you can see that I calculated the states. So in my system, now I know inside the system how all the states are behaving within the system. Not only the output, I know the states inside the system, how they're behaving. Now what we want to do is we want to calculate the output. How do we calculate the output? We come back to the equation. Here, I know y is equal to c multiplied by x. So therefore, I have x, I can calculate y. Y of t is going to equal to 1, 1, which is the C matrix, multiplied by x, which is 1 minus 2 e to -t, and e to -2t. And if I multiply these together, this term is going to multiply by this, 1 is going to multiply by this, I'm going to get 1 minus 2 e to -t plus e to -2t. And this is my output y of t. Okay, I hope this example is clear. Again, this also shows us the advantage of using the state space. If I were to use a transfer function, I would have the output y of t, but I will have no idea what the states or how the states inside the system is behaving. Using the state space, I'm able to not only calculate the output, but also I'm able to see how the states are behaving, and I can plot them and study them. Okay, I'm going to stop at this module here to make it shorter. We'll continue with the next module with another alternative for representing phi of t.